Okay, let's get started. Assignment number 5 is due April 20th at noon. Presentations begin on Thursday. Again, please email me everything within 24 hours prior to your presentation. Also, please make sure you have an opportunity to plug in your computer to the system up here to make sure everything works out. Now, when you come in on your presentation day, after you get everything hooked up, one of the first things I'm going to do is give you this. And this is a little USB drive that contains the recording software on it. And so you'll just plug it in, and I'll show you a particular file to open up that Camtasia relay file. And again, what's going to happen is it's going to actually record everything on your computer using your microphone, and it's going to record your screen. There will not be a webcam set up with your computer, so we will not have live action video like what we do with our recordings. But that's fine. And then once the recording's done, of course, you'll have to stop. And then you'll be given an opportunity to transfer the files to this. Initially, Camtasia Relay records everything on your own computer. And then after you're done, you have the opportunity to transfer everything to this. And that's what you'll need to do so that I can take it back to my office and then upload it to a server that will do some post-processing with it. Okay. Are there any questions? Also, I guess just a reminder, remember, you need to do 3 of the 7 assignments given by the other presenters, corresponding to our presentation that we have coming up. Okay, if there's no questions, then let's talk about numerical integration. So when I was writing up these lecture notes, I decided just to simply jump right into one of the main functions that does numerical integration in R called integrate. I've been using this function now for about over 10 years, and I've had a lot of success with it. I really like it. This is a function just for, let's say, integrating with respect to one variable. So please take note of that. We'll talk about if you want to do multiple integration later on. And this is the syntax for using the function. So the f argument, let me get my out. The f argument corresponds to an R function that you have written corresponding to the mathematical function that you want to integrate. Okay, red. So there's f. So it kind of works a little bit like, when we were working with the optimum function in R, where we had to write an R function to represent a mathematical function that we wanted to optimize. Then, as you might expect, you put in your lower bound and your upper bound with respect to what you're integrating over. And then we have some other options as well that we'll kind of talk about as we go along. In particular, for example, rel.toll. Like on most computers right now, this will be 0.0001, which controls the accuracy that you want your integral to be. Now, the function that you write to use with integrate has to be able to accept vector input. So, for example, like if I were to integrate a beta distribution, I could use the d beta function, and I know that with the first argument of d beta, which is x, I can put in, let's say maybe 0.2, 0.3, 0.4, and the density is going to be evaluated at all 3 points. So that's a key aspect that you have to write your function, and generally that's the way we do it, so that you can, so that it accepts vector input for what to evaluate your density. And for us, it's going to be a density, what you're going to be evaluating your density at. Similar to what we saw with the optimum function when we had constraints, you can use inf for infinity for now your lower and upper bounds. Okay, so let's just simply take a look at an example here with a beta distribution. Let's say I have a beta distribution with the first parameter, which we often call alpha, but I call A here, of 0.5, And the second parameter, usually called beta, I'm going to call it b, it's going to be 2. Just going to jump ahead to what the distribution looks like. So you can see it's a heavily right-skewed distribution. Of course, beta distributions are between 0 and 1. And what I'm going to be interested in doing is integrating x for my beta distribution from 0.1 to 0.5. And so it's the area that's nicely colored in there. Okay, so how do I do this? Okay, so I write a function that I need to use with integrate. So I just simply call it beta.density for the lack of a better name. 3 things I'm going to pass into it. X, well, I'm going to evaluate the density at. And then the 2 parameters for the beta distribution, A and B. And since it's already available to me, I just simply use the dbeta function to actually return the density. In other situations where maybe you have a different kind of distribution, you might want to actually obviously type in the actual formula or expression for the density itself. Then, of course, what we could do first of all, just to verify that, what I like to do often when I'm working with a particular probability distribution, let's verify that if I integrate over the entire range of my random variable, then indeed that I do get 1 back. So let's do integrate f equal beta.density, lower bound 0, upper bound 1. There's a ... argument in integrate, so I can pass in my A and the B. And notice I get a value of 1. And it also gives me a measurement of the overall error possible with this numerical integration. Obviously the error is quite small, so that means, hey, I have a lot of confidence that indeed that this worked out well. Well, let's integrate over a specific region from 0.1 to 0.5, and as you might expect, the code is just about the same, but I just replace, this is on page 3, lower and upper with the corresponding values, and I get a probability of 0.425, small error. I can check that with using the p beta function. So p for probability, beta for beta distribution. And so what I'm going to do is find the probability that x is less than 0.5, and subtract off the probability that x is less than 0.1 using the p beta functions, and what do you know? I get the same thing. That's good. So you can see, using integrate functions not that difficult. I'm not going to go over the code for how I drew the plot there. You can take a look at it on your own. It's not too difficult. The main function that you may not have seen before is the polygon function. And then what allows me to color that area in blue. Just a nice little useful function, especially for those of you who teach in Stat 218 and you want to do a nice little R plot. Well, not necessarily having them use R, but do a nice little R plot to demonstrate, find probabilities underneath a curve. That might be helpful. Okay, now, as with any other function, you can always save your results. So I'm going to do exactly the same implementation of integrate on page 4, but I'm going to save the results into an object called ans for answer. And so we can see basically what integrate was printing for us was the default printing method. So if I just say ans, you can see the same things we did before. Inside of ans is actually a list, and it has different components where the value component is the actual interval value. One reason why I want to point this up is because I once had without going into all the details, I once had a student who needed to do some numerical integration for to find highest. What was she doing? She was finding an equal-tailed credible interval, and so it was a weird distribution. She needed to integrate, and unfortunately, she did not understand how she could save the results from doing the integration. So you can learn from her issues, and that's how you can do it. Okay, so perhaps I should have this earlier. This is what we were actually doing for the integration. Well, what about moments? Well, it's not as simple as simply saying, inside of this right here, let's say if I wanted to find the mean, I cannot say x times beta dot density. I can't say that. Instead, what you would need to do is actually write a new function that does that evaluation that you want. So let's say if I want to find the mean, I'm going to create a new function called beta.density.mu, where it's the same as before, but now I have an x asterisk there with d beta. So if I do the integration over the entire region, of course, I get 0.2. And from your stat 883 days, you know that the mean of a beta random variable is alpha over alpha plus beta. And so if we actually evaluate it, we of course get exactly the same thing. So that's nice. What about the variance? Well, you might be thinking, well, why don't we just go ahead and find the second raw moment, expected value of x squared, and take that, subtract off the expected value of x squared. But when you do stuff in a numerical manner, you don't need that. And instead, you could actually just simply go directly to the expected value of x minus mu squared formula. And that's what I did here. So I put x minus mu caret sine 2 asterisk d beta. Notice I do have to pass in mu in order to do this. At least that's the way I chose to do it. And my variance that it gets 0.045, which matches up what we know what the actual formula is. So not too difficult. Okay, so that's just an introduction to how to use the integrate function. But now let's talk about how is this numerical integration being done. And to do this, we're going to actually talk about a simpler way to do numerical integration called the trapezoidal rule, and that's going to lead into more complicated ways to do integration using quadrature. Yes?
Quick question about the subdivisions that we had in the function. Yeah. Are those like the small divisions that you integrate up?
Yeah, so, eventually we're going to talk about that, but we can briefly talk about it right now. Okay. So you can imagine I have basically, I'm trying to find the area underneath that curve, and I have two subdivisions. And so you can specify a max number of subdivisions. Right. The 100L that you see as the default, let's go back to that code in case you're not aware of this. Whenever you see an L right after a number like that, that tells R that this means integer. So, how this is not as big of a concern nowadays as it once was. But, to represent something as an integer versus, let's say, floating point notation, integer is going to take up less space. And so that's why you still will see in some aspects of R an L right after a number to emphasize, hey, this is an integer.
I guess because of this we cannot, intuitively that's the reason because why we cannot do x times whatever to find the...
No, I think it's more of a syntax issue.
Right, like the way the integrate function is set up, I think, because it'll do integration for each of the subdivisions, kind of.
At least for me, I don't think it has anything to do with it. So we can talk more about it after class if you want to. Yes?
When you pulled out the different items from what you called ants, what does the OK mean? Just that it...
Obviously I skipped over that. And it just means everything worked out fine. Everything was okay.
I didn't know if it was the specific. Okay.
I don't think I've ever, at least from what I remember, I don't think I've ever had anything different from that. Yeah. And I've looked at the documentation for it. I have not necessarily seen like a list of messages.
Okay. Maybe
just if you do get something other than okay, I would be concerned.
Problem. Okay.
Maybe we can do x times beta dot density and see we might get some other.
Well, I think it will say a syntax error because it's looking for a function. Okay, so the trapezoidal rule, and what often numerical integrations base upon is trying to approximate the function of interest with easier functions, and trying to then find, let's say, the area underneath that function in different subdivisions, as we were kind of seeing there. So with respect to the beta distribution problem again, if I want to integrate from point 1 to point 5, I don't know why, at least from my angle, that's not coming up very well. That is a negative there. And what simply happens is this: if I want to approximate this region from point 1 to point 5 by 2 trapezoids, this is what would be done. Okay? And all you need to do now is use the regular old formula for the area within a trapezoid. Use that for that region, and then also use it for that region, and there you have an approximation for the area underneath the curve. So it's as simple as that. Notice, though, that essentially what we're doing is using a straight line approximation to a curve. And so as you might expect, then, that straight line approximation is not going to be as accurate as if you were to use some other kind of approximation, maybe something that's more flexible. And in fact, that's what quadrature does. Okay? But let's just take a look at this to help motivate the ideas behind quadrature. And so let's take a look at the pragma package again. Remember, we saw that with the numerical differentiation section. Pragma stands for practical mathematics. And I'm going to get a sequence of numbers from point 1 to point 5 by point 2. So in other words, it's going to provide point 1, point 3, and point 5. And there happens to be a function called trap-z that does the trapezoidal rule for numerical integration, where you put in your x values, you put in the corresponding y values for those x's. So notice I'm evaluating my density at x dot values 2. And then it does all the math nicely for you, finds the area of those two trapezoids, you get 0.458. And again, if you remember, if you're using a more accurate method, we got 0.4254. So we can see we're a little bit off. That's not too bad. Now, let's actually kind of, you could say, do this by hand. So what's the area of a trapezoid? 0.5 times the width of the trapezoid times the first height plus the second height within parentheses there. So in other words, again, for emphasis, here's the width. So the width is 0.2. Here is, let's say, height 1. Here is height 2. I add the two heights together, take it times the width, take it times 0.5. So when I do all that, so notice how I get my heights using the d beta function. Here's the plus there, so this is, you say h1, here's h2. I do all the math and I get exactly the same as what the trap-z function gave us. Now the reason why I wanted to actually emphasize this is so that we can rewrite it a different way. And then again, this is going to help us motivate how the quadrature stuff works. So now what I could do is write it so that I have 0.5 times the 0.2, just like what we saw before. Let me do a little highlight there. And then I'm going to multiply through to get the first height. And then I'm going to also do the same thing for the second height. And then lastly, just because I really like the color, we'll do the third one as well. I hope all of you remember to bring your crayons today. Oh, and I'm horrible at coloring, as you can see. Hopefully that makes sense. You know, I just combined some stuff. And the key thing is to realize is that basically we have weights here, where we're weighting the height of our function that we're interested in integrating. We're weighting them. And through just simply using these weights, and I emphasize this more down here, here's my weights again, that's how we're essentially doing this. So if one wanted to, then one could write it out like this. Take the sum of some weights times your function that you want to integrate, evaluated at particular points. And that was for 3 points. So again, notice the approximation there. So that's what Gaussian quadrature does. It has a nice way to figure out what should be the weights and at what points should you evaluate your function at. Okay? So I think all of you, when in 971, you at least heard the term quadrature. Does that sound familiar? Okay. But just, at least from me, from my talking to students, some in this class and also some not in this class, you don't necessarily go over the details. You might, maybe you're told essentially you're doing that. Does that sound right? Mm-hmm. Okay. So what we're going to do today is give some motivation for about, well, where does the W's come from? Where do the X's come from? And then eventually, though unfortunately we probably won't get to it, I actually have a nice, a very simple generalized linear mixed model where at the end of these notes, where what we want to do is find the maximum likelihood estimates for the corresponding parameters. And we're not going to use proc-glem mix to do that. We're not even going to use the the function glemmer, which is kind of the equivalent in R. We're just simply going to use optim and Gaussian quadrature. Okay. Excuse me. So let's look at a simple Gaussian quadrature setting. Let's say that I want to approximate for any, well, for a particular function f of x. I want to approximate this integral from -1 to 1. And I'm going to use 2 points of quadrature to do this. Sometimes people call these nodes or evaluation points. And I want to do this approximation actually exactly. I mean, I want to get the exact answer for polynomials up to an order of 3. So to figure out then what the w's and what the x's should be, I can do the following. Let's say that my f of x was actually equal to 1. So the integral from -1 to 1 of 1 dx is equal, of course, to 2. And so what I'm going to do is set this equal to 1 weight times f evaluated at some point x1. Since f of x is 1 here, that would mean it's just simply 1. Plus another weight times f of x2. x2 is just some point that I'm going to pick. And of course will be 1. Then let's also look at the same integral, but now f of x is equal to x. And so that is equal to 0. And if I were to set it equal to w1 times my f of x1 plus w2 times the f of x2, that's what I get. And I keep on going to x squared and x cubed. So now what we have here are 4 equations and 4 unknowns, where I'm focusing on the part that is highlighted in yellow. I have 4 equations, 4 unknowns. I can go through the math, and I can actually solve then for w1, w2, x1, and x2. So what that means then is that for any function that's being integrated from -1 to 1, and as long as it's not higher than an order of 3 for the polynomial, I will get an exact answer by simply taking w1 times f of x1 plus W2 times f of x2. On your own, try that indeed does occur with that particular function, integrate. Now you might be thinking, okay, well, it's not often that I integrate from -1 to 1. This is kind of restrictive. Well, no, it's actually not. Remember, your Calc 1 days where you did a U substitution? Well, you could do a U substitution here to transform the limits of integration to what you need to get to -1 to 1. And still, of course, then get the same value for your integral. Okay. Any questions so far? Okay, so let's look at, there's a number of different kinds of ways to do a Gaussian quadrature. We're going to first focus on one called Gauss-Legendre, I believe that's how you pronounce it. And this is focuses on integrating from -1 to 1. And the whole idea now is to say, well, maybe, if I go back here, remember how this was kind of a limitation here where we were using this essentially a linear approximation at those areas there. We were doing a linear approximation at that line. And the idea here then with this kind of quadrature is now, let's do something other than linear so that we get something better there. If I get something better there, that means I'm going to get a better approximation to my integral. So what we can do is set up some Lagrange polynomials. So let's let L sub I of x be equal to this expression here. To help you see what that means is, let's say that n is equal to 3 then what you're doing here is that, well, let's say that we are looking at L1. What you're doing here is you're taking x minus x2, x minus x3, all over x1 minus x2, x1 minus x3. So these x's are points that you're going to evaluate at. So, like getting back to that beta distribution example, x1 could be 0.1, x2 could be 0.3, x3 could be 0.5, for example. And then what we can do is that we can actually approximate the actual function of interest, f of x, by doing then a sum of these polynomials times your original function itself evaluated at your x of I. So again, think of it in terms of if n is equal to 3, you're simply going to have 3 terms there. And that's going to give you an approximation to what the height of that curve will be. Well, if we were then wanting to integrate from -1 to 1 for f of x dx, well, let's put it in terms of this approximation. So I take my sum and I put that into my integral where I had f of x before. I can rearrange some terms. And notice what we have here. We have this written as I had originally showed you with quadrature, in terms of you're evaluating your function at particular points and you're taking it times weights. Well, what are my weights? Just integrate that Lagrange polynomial. So that then, since this is actually, let's see here, come back here. Obviously, this is an approximation here. And if I wanted to, I could put an equal there and put a remainder term there, right? Okay? Well, how you choose then, or I'm sorry, you want this remainder term to be as small as possible. And I guess that's kind of a compromise here when I was writing out my lecture notes. I decided not to go into the details behind how you would actually choose, I decided not to go into details behind this remainder term. Instead, I'm just going to say that you can choose your x values in a way such that this remainder term is as small as possible. And the way that that's done is through the Legendre polynomial, is using Legendre polynomials for that. If you want to see the details, take a look at a numerical analysis book. It's the one that I used. Okay, so let's take a look at an example now with the beta distribution. We're going to use this kind of quadrature for that. Again, I'm going to use the Pragma package. So if you haven't already loaded in there, you would load it now. And I can use a function called Gauss-Legendre, where I want 3 points of quadrature. And I'm going to integrate, and I want to deal with not -1 to 1, but a different range. And I can specify this different range here, and it does all the nice little conversions for you by specifying A and B for your lower and upper bound respectively. Then your x values that you're going to be evaluating your function of interest at are automatically calculated for you. So 0.145, 0.3, and 0.454. And then you also have your weights as well automatically calculated for you. And so now if I were to take then the sum of all these weights times now my d beta function evaluated at those x values, I get my approximate value of my integral, which is very similar, 0.4254, which is what we got before. So you can see how accurate this is. I think if you think of it from this perspective, I think it's it's really cool that all I'm doing, I just need to be able to evaluate my mathematical function, multiply it by some weights, and I got the integral. Well, as you might expect then, if you use more points of quadrature, then you're going to have a more accurate representation of the integral. So if I did 7 points, I mean, this was already pretty accurate to begin with, but if I did n equals 7, then I get 0.4253, which is, actually, if I round to 4 decimal places, I get exactly what the integrate function gave us before, and also I get what the p beta function would give us. Okay, so as I said here, this type of quadrature is defined over a range from -1 to 1. And I go through some details here that you can look at on your own that shows how some of this stuff was done. And I'll let you look at that again on your own. Let's now skip down to page 14. There's other types of quadrature out there. This is actually just a screen capture from Bloomfield's book, which shows the different kinds of quadrature in terms of where they are good in terms of intervals. So like -1 to 1, or maybe -infinity to infinity, and also, and I think this is kind of confusing in Bloomfield's book. If I come down here to page 15, again, I'm interested in this particular integral here, the integral a to b f of x dx. And what we can do is basically break this f of x into 2 parts, a w of x and a g of x. This w of x is not the same as the weights that we've been talking about before. And that's, unfortunately, I think Bloomfield makes it kind of confusing there. And what that wx then represents is what's in this table here. So if you could somehow arrange your f of x function that you're wanting to integrate in a format so that you have maybe, let's say, e to the -x squared as w of x, and then everything else is put into g of x, then Gauss-Hermite type of quadrature is going to be very good. And so then, what you're hoping to do then is then again approximate it by some weights where this wi is not connected to this w of x at all, not directly, times now g of xi. Now, why do you think I picked on this one right here? Hopefully I don't have the answer there. I guess I do on page 15. Well, why did I pick that one? Well, because often in a, let's say like a generalized linear mixed model setting, you're saying your random effect has a normal distribution to it. And in your likelihood function, you're going to see some normal distributions pop up. Of course, with a normal distribution, you're going to have a term that has e to the negative, let's say x squared, essentially, in it. So if you could rearrange stuff in your likelihood function so that you just had e to the negative x squared there, Gauss-Hermite quadrature represents a great approach. And in fact, when writing up these lecture notes, I decided to play around a little bit with procolumics, and I hadn't ever used procolumics before. I used stuff from R, and what do you know? In the output, it says Gauss-Hermite quadrature was used. So, now what does exactly integrate do? Well, it doesn't use this kind of quadrature. Unfortunately, it uses Gauss-Kronrod quadrature. I have to admit that I hadn't heard of it before until I was looking into the details of integrate. As I think I said at the beginning, I had used integrate for over 10 years, and I knew about what numerical integration was. I was satisfied with looking at using it, and always worked for me. So I didn't necessarily look into the details behind how this function worked. And then when preparing these lecture notes, of course, I wanted to look into the details, and I don't see this Gauss Kronrod quadrature discussed as much, but from what my understanding of it is basically it says it's adaptive in a way that basically it has a way to maybe you end up using, let's say, 10 subdivisions, let's say. Well, it will actually it will do, let's say, 10 subdivisions for your integral, and then it will actually do some more subdivisions to estimate an error. And that's why you see that estimate of error always whenever you do integrate. So it just essentially goes a step further to see, okay, well, just how good it was. Also, I often see the word adaptive used with Gaussian quadrature, though, to mean something in addition. I think this is also what integrate is doing. And that is, you don't necessarily, how should I point it? Let me go back to my plot here. So, let's say, we were just simply using a straight line approximation here. Now, you can see that obviously here, it doesn't do as good of a job as here. And so what one could do, especially if you have some kind of measurement of error, as that procedure does, is say, I can see that I'm off there. So what we could do is instead, how about we put another line there, so we have unequally spaced areas here, and now we approximate, I think you get the point. We can make smaller subdivisions. If I make smaller subdivisions, the smaller they are, the more the better approximation you're going to get. And so that's why I often see the word adaptive is used, is to represent that. And I believe that's what the integrate function is doing. Okay, so let's take a look at an example of using a Gauss-Hermite quadrature. So this is taken from McCulloch and Searle's book on generalized linear mixed models. This used to be the book that was used for Stat 971. This is actually at the towards the end of the book when they talk about some of the computational details. And so I just simply, simply want to approximate this integral here. Notice how it's nicely set up. So here's my w of x, here's my g of x. Okay. And so if I use a particular function, the pragma package, and I specify I want 3 points of quadrature, I get my x values to evaluate my g of x at, and then also I get my weights out, similar to what we had saw previously. And so that if I were to simply, excuse me, get all choked up when I teach now. If I just multiply my weights by my g of x evaluated, at all those points. So notice how I pull them out here. I get my integral, approximate integral value. If I compare that to what integrate gives me, well, what do you know? It's the same. Just so I was curious, since obviously you can do this by hand, and just to make sure that you understand that you can do a lot of this stuff symbolically. I've kind of talked about this with respect to differentiation. Here's just in Maple my code to do all this symbolically, and I get the same answer. Yeah.
So the W's are the Li's that the Lagrange are those the integrate.
No. Oh, the W of the W sub i's, yes.
Yes. So the ones that we got in the output, like the W's that you gave.
Yes. Okay. So that was with 3 points. Now, of course, that doesn't mean you're going to get the right answer all the time if you use 3 points. So let's say if I change my function instead to 1 plus x to the 6th power for my g of x. 3-point quadrature, though, if you go through all the details, gives you 3.76. If I do 4-point quadrature, I get something quite different. I get 5.09. If I use the integrate function, 5.09. If I do it all symbolically, 5.09. So you can see, again, the more points of quadrature you have, the more likely you're going to get a good approximation. Now let's do this stuff now with a normal distribution. So let's say that I want to find the expected value of x for a normal distribution with mean 0 and a variance of sigma squared. If I put this into the Gauss-Hermite format, what I can do is do a little transformation, let u be equal to x divided by sigma divided by square root 2, so that I can just get e to the negative u squared in there. That's all I want. Notice here's my e to the negative u squared now. And some things cancel out. So I'm left with this as my integral. So this equals my original integral. I want to approximate this now with 2-point Gauss-Hermite quadrature, where I'm going to just let sigma to be equal to 10, so we can do this stuff numerically. Excuse me. Now note that this part right here kind of serves the role as my g of x. I'm going to call it g of u. And so I use the corresponding function. I get my u values out. I give my weights out. And if I take the sum of my g of u times my w, I get 0, which of course is the expected value of x for this normal distribution. Once again, I can show the exact same thing with the integrate function too. That takes us to page 20. Well, what about multiple integration? This is sometimes called cubature instead of quadrature. There are a few R functions out there that do multiple integration. In particular, there's one called adapt integrate. I'm not going to go through all the details behind how it works. Let's just apply it to a multivariate normal setting so that we get see how it's done. And let's say that my multivariate normal looks like this. I'm sorry, it's a bivariate normal. Mean vector is zeros, and the covariance matrix then is just basically an identity. This is what the actual distribution looks like in 3D. I'm sure all of you are wondering what it looks like. And what I want to do first of all is verify that the volume underneath that surface there is actually equal to 1. So there's a nice little function R called DMV norm, which finds the density for multivariate normal. And that's in the MVT norm package. I'm going to say library cubature as well. And I write a function here that I want to integrate. similar to what I did with the d beta function before. And then I just simply say adapt integrate. I put f as my my r function. It has the bivariate normal density in it. For my lower limit argument, you can't use infinity with this function, unfortunately. So just because of what we know about multivariate normal, I decided to go from -4 to 4 for the first. I'm sorry. -4 to 4 for both, let's say, x1 and x2. And you just specify them as vectors in your lower limit and upper limit arguments. And my integral is approximately equal to 1, as you would expect. You could go from -10 to 10 as well, and you get closer to 1. Okay, so you could also go through the various moments too. I did this here. Look at it on your own. You could also find particular probabilities too. I don't really think it's worth our time since we have a very limited amount of time to go through those details. Of course, there are other ways to do numerical integration, using MCMC methods, especially if you have multiple integrals that you want to do. MCMC methods are often easier to use. Okay, so let's go to this last example, which is a lot sooner than I had anticipated, but that's good. Do note, as you probably have already guessed, is that there's not going to be a particular assignment corresponding to this section here. So this is essentially the last time that we're going to see this in this course. There's not necessarily any way that I can hold you responsible for going through these lecture notes. I hope you do. But this is more for fun right now, given where we are in the semester. And so one of the things I wanted to do then was kind of put some of this stuff together that we've been doing since the high performance computing section. And so I thought, well, let's just look at a generalized linear mixed mouse situation, which all of you have experience with in 1971. And of course, then when you start doing this kind of stuff, you want to start very basic. So here is my simple logit model that I'm working with. So the logit of pi sub I is equal to beta 0, which is a parameter that we want to estimate, plus b sub I, and b sub I is my random effect. So you can imagine maybe I'm sampling, I don't know, maybe n different individuals, for example. And I want to include those individuals in there simply as a random effect. These y's are going to be distributed in a binomial, where the number of successes is the number of trials is n sub I. Each y sub I has potentially a different probability of success. So, well, what would be then the ith contribution to the likelihood function? Well, this is where I have my binomial distribution. So you could say, for example, this would be, let's say, f of y given b, for example. And then this would be f of b for my random effect. So this is, in here is my joint distribution for y and b. Now what I need to do with this likelihood function is actually integrate out b. And we can see that it's not just a simple normal distribution that you're going to have to work with, because pi sub I is dependent upon b itself. And so that's why numerical integration is a nice way to approach this. So my log likelihood function then is just then the sum of the log of the individual elements itself. And you can play around with it a little bit until eventually you get to this point here. And again, I want to approximate this integral. I'm going to do that with integrate shortly. My maximum likelihood estimates, though, that I need beta 0, an estimate for that, and also the variance of the random effect. So I have two things I need to find maximum likelihood estimates for. And so what I need to do is maximize this function. And as you know in Set 971, again, the thing that makes this difficult is the integral. So the way that you can do this in R is use the GLMER, or we'll just call it GLMER function that's in the LME4 package. Doug Bates at the University of Wisconsin is one of the big authors of this particular package. It's one of a few different packages that allow you to do generalized linear mixed models in R. I think this is probably the most often used one. We're going to look at how to do that. We're going to look at how to get the maximum likelihood estimates using that function. We'll also look at proc-limits, and then we'll also do it essentially, you could say almost using by hand formulas. First of all, we need some data. So let me actually go over here to R, or 10 first of all. So I'm going to get a sample size of 1,000, you can say maybe people. I'm going to set beta 0 to be 1, sigma to be 2, and I'm simply going to generate some data, where for each of these n individuals, there's going to be 10 trials. Okay. I'm going to set a C number so I can reproduce my results. Then I'm going to generate my random effect for all n individuals. From that, then I can use the p-log-gist function to find my probability of success for every single individual. And then I'm going to simulate my binomial response for all individuals. So those are all my binomial responses. Okay. So to do this, first of all, in R using the glmer function, first of all, I have to download and install the LME4 package. LME stands for linear mixed effects. Then I'm going to put my results into something called mod.fit20 for the lack of a better name. And I say glmer formula equal. If you've used, all of you have used now GLM before, that function R, this has a very similar format where I say my number of successes, which is in Y, divided by my number of trials, tilde. Since I don't have any covariates in my model, I can just specify 1 to get my beta 0 estimated. And then to do the random effect, I can do 1/individual. So again, I have 1,000 individuals. So if I just look at individual itself, you can see that I have numbers 1 through 1,000. And the 1 there basically kind of corresponds to, well, you know, you're not estimating a random effect corresponding to a covariate, just similar to how we have a 1 there. The number of points of quadrature, I'm doing way too many here, but I just decided to put this in here, 20. Weights, number of trials per observation. And then family equal binomial, link equal logit. So if I go ahead and estimate this model, doesn't take very long at all. And this is what I get. Let me actually go back over here to this. Okay. So here is your sigma hat squared. So again, for your B random effect, this has a normal distribution to it. That's your estimate of your estimated variance component. And here is your beta hat 0. Thing to notice here is that these are very close to what their true values are. Remember, we set beta 0 to be 1 and sigma to be equal to 2. And so again, whenever you're, this is why I like to do this in a teaching situation like this, what this is telling me is that I know I'm getting what I should. If I wasn't getting this, then I'd be worried if I had programmed this incorrectly. Okay, so let's look at then how we can do this without that glmer function, and we were to use integrate and optim. I think this is very helpful to do because it helps you, get beyond just using proc-limits or the glmer function and make sure that you understand what this likelihood function is and what you're actually doing to it. So what I do first of all, actually let's do this. Let's look at the log likelihood function. And let me do a split screen here. Okay, so basically what I need to do, I need to create a function that Optum will use that evaluates this function. So, first of all, there are two parameters of interest for us, beta 0 and sigma. I'm going to put them into a vector, just like how Optum needs it. I'm going to put in my y data and also number of trials per observation. Then I'm going to pull out beta 0, pull out sigma, get my sample size. I'm going to initialize a vector that's going to have every contribution for the ith individual to the likelihood function in it. Every contribution then, notice I'm summing over I equal 1 to n. So what I'm very concerned about is this integral right here. So I'm going to say integrate basically something that I've, a function called my.func. Let's look at my.func. This is how I put this integral, or the function I'm integrating, into R. I'm integrating over something called B. Put in my, I need to pass in my data. I need to pass in my current value of beta 0, my current value of sigma, and also the number of trials. Obviously, I have these pi's here. So I'm going to write I'm going to create an object called pi.i that takes p logis beta 0 plus b. Remember how we simulated our data? Well, that's the same format. That's how I formed my pi's before. Next, well, then I put the whole function I'm integrating. Take pi.i raised to the y power, 1 minus pi.i raised to the number of trials minus y power, times now my density for my normal distribution. So that's what I'm integrating. I'm going to integrate that from negative infinity to infinity. Notice I just need to pass in the ith data value into that. And then immediately I'm going to take out from integrate the value. Remember when we looked at the components of what integrate returns to us? It's a list where the value component contains then the integral value. So I'm just immediately going to pull that out. And then now I can form the rest of my log likelihood function. I have the log to worry about, I have the sum to worry about. So what I'm going to do is take the log of every component that's in those individual elements of that likelihood function, and then I sum it. And so that's how you find your log likelihood function. Okay, so now let's actually evaluate the log likelihood function at the true values, just to make sure that this works. And I get a value of negative 5,216.237. We'll come back to that shortly. Now using Optum, I'm going to find my maximum likelihood estimates. So I have some initial estimates for beta 0 and sigma. And I cheated here. I put in what the true values were. That's often what you do at the very beginning when you're trying to do something, again, from a teaching standpoint, because you know that this should work out. You know, there's other ways that you can come up, use to plug in starting values if you wanted to. My function that I'm going to optimize is called log.lic.int. Remember, I'm going to use BFGS as the method for optimization. And I pass in the other information I need, and I specify hash equal true. So that then, what's returned? Here's beta hat 0, and here's sigma hat as well, which are identical to what we got from the GLMER function. Essentially identical. Notice the value here, negative 5216.22, which is very close to what the true value is. Now note that the GLMER function gives me a log likelihood function value as well. And the best that I can figure out is that basically some constants are lost, because the constants are probably often not necessary, so some constants are lost, and so that's why they don't match up. Notice we had convergence. Here's my Hessian matrix. So if I take the negative of that and invert it, I get my corresponding estimated covariance matrix. So what we have here for 0.0717 then is my estimated asymptotic variance for beta hat 0. And then we also have the estimated asymptotic variance for sigma hat as well. Now I think it's good just to review, why is this important to do? Well, in your actual research that most of you guys will be working on, you're not necessarily going to have procoglymics or GLMER to fall back on and implement what you're doing, because after all, you're doing research. Since this research is not a function necessarily that's going to do this stuff, and you're going to have to write your own function that maybe will fit a particular model. Here, this shows you how you can take the basic building blocks of like using integrate function, using the optimum function to do what you need to do for whatever model that you might have of interest. And so that's why this is, I think, very useful. Well, you could do all this Gauss-Hermite quadrature stuff directly. I think you get the point. I'll let you look at it on your own. Of course, you get the same answer, or just about the same answer. Here's what the actual likelihood function looks like. And again, in a research setting, you want to again start simple and actually take a look at it to see if it makes if the answers that you got for the maximum likelihood estimates make sense. And indeed, if you look at the contours there where the maximum is going to occur, yes, what I did here does make sense. And lastly, I debated whether or not to do this. I did it in SAS. I think all of you probably know how to do this kind of stuff in SAS, so I won't go through the details. The key is that you get just about the same results. I had to edit a lot of the output because it's just so much output. It is interesting to note that the log likelihood function that's evaluated the parameter estimates as returned is different from what we got in two different places already. So again, they probably just threw away some constants, not necessarily the same constants as what GLMER was. So some final notes on numerical integration then. So as we saw, the integrate function has no problems with dealing with infinity as one of the limits of integration. Here's where I talk about the subdivision stuff that we've already kind of talked about as well. I'll let you look at that in more detail if you're interested. I guess I emphasize this here again. Pay attention to the relative error that's given to you by integrate. Obviously, if that error is large, you want to be very careful. Let's see. There's more integration capabilities of R. Take a look at the numerical mathematics task view. And as far as I know, there's not a way to do symbolic integration in R. So. So then that concludes the numerical integration section.